Everyone, Michael Roper here with Smart Buildings Academy, and welcome to our podcast today, where we're going to be discussing valve sizing. The title of our podcast this morning is going to be The Art and Science of Valve Sizing. We're going to be decoding the mysteries of valve sizing on this Friday morning. So let's go ahead and get started. What we're going to do first, before we can talk about valve sizing, what we need to do is kind of go over the basics of a valve and the different types of valve that are used in our building automation system projects. So what I want to do first is I want to just give a brief overview of the parts of a valve and how those work. Okay. So the parts of a valve, this over here is an example over here on the right. This is an example of a globe valve or a ball type valve. This picture over here, the main casing of the valve is going to be called the body. All right, that's going to be our outer shell. It's going to contain all the components that we'll use to control this valve over here. All right. The bonnet is going to be the cover on top of the valve body. I don't know if you can see. I'm going to get my laser pointer here so we can see it better. Up here is going to be called the bonnet. All right. So this terminology is important here to understand. This is the cover on top of the valve body that houses the stem and other components like the disc and the seal and all that other all those other components too as well. And that's going to be called the bonnet. All right. We also have the stem. Now the stem is a very important piece. That's this metal vertical rod that's going inside the valve body here. It's going to extend through the bonnet and into the valve body. This is what's going to control the opening and closing of the valve, okay, for water to flow through it. Now, we also have the disc or the ball. Now, this one, what I talked about before, this is a ball valve, all right? So this is a movable part that regulates the flow of fluid, which will be water in our case, through the hydronic system. Okay, that's going to be the ball, or it could be a disc. I'll show you an example of what a disc looks like here in a second. We also have a seat. All right, so this is where the disc or the ball rests on to control the fluid. It's usually made out of rubber or plastic, and it makes a tight seal. So if you ever hear somebody that has to repack a valve or something, the seals went out, that's what they're talking about. And that's just basically prevents any leakage through that valve body. That's going to be called the seat of the valve. And then, of course, we have the way we control our valve bodies is with an actuator. Okay, this is used to control the valve disc or the ball, okay, up and down. Now, this is an example of a disc over here, if you could see that. This is a disc type a valve over here. All right. Now, we also have some fittings that can be connected to the valve body. These are going to be usually a flange, like we see right here. This is a flange with a circular shape. It's got holes in it where we bolt it to the pipe. And we also have the threaded over here. This is just national pipe thread to where we could thread these into a pipe. Okay, so those are the basic parts of a valve. This is good to know whenever we're sizing a valve, just to be aware of these different parts and pieces for the valve. Okay. Now let's talk about different valve configurations. Okay, we got the two-way and we can go three-way with our valve configurations. So the two-way valve's pretty simple. Actually, it's really simple. Water enters from one side and flows through the other. Okay, so as we can see in this example here, water is going to enter through the supply, go through our coil. This can be a chill water or heating water coil, or even a steam coil. And it's going to exit out of there and enter into one port and leave out of one port. All right. Enters port A, leaves in AB. All right. The disc or the ball is rotated or moved to increase or decrease the water flow. So we got the ball that's inside this valve. And depending on how much we open or close that, will increase or decrease our flow through our system. These are commonly used for isolation type applications. They could be also used to control coils as well, okay, in variable type hydronic systems. So that's where we'll use our two-way control valves. Now, the other ones are three-way valve, and we actually have two types of three-way valves, all right? So the first one we have is a mixing valve here, okay? The mixing valve is going to be this example over here on the left. And what that does is fluid enters two different zones and then comes out one common port on the end. So if we have our supply entering our coil here, we have port B it can enter. All right, that's going to bypass the coil, basically, is what port B does, or it can flow through the coil and leave and enter port A. Okay. Now, if we're going to mix these two together, we're going to mix the going through the bypass on port B with port A, and those are going to mix together, coming out back to the return, back to the chiller or the boiler. Okay. So mixing valves just mix fluids, and they're coming from two different zones, and then they're going to leave out of one common outlet port. The other type over here on the bottom right is called our diverting valve. Now, this fluid is from a source that enters one port and then it's directed or diverted out of two ports. All right. So over here, we have our supply entering from our chiller. All right. That's going to be AB right here. And then at AB, it's going to go one direction on A out of port A to the coil, or it can go to port B back to the return, back to the chiller or the boiler hydronic system. So we're diverting water away from the coil here, and it's going back to the return. Okay, so it's entering a common port and diverting two different directions here. Okay, that's what that means when we talk about a diverting valve. Okay, these are commonly used for zone control, bypass, and also mixing applications. All right, so let's talk about the different valve types, because there's several different valve types when we're talking about valve selections. The first one we have here is called the globe valve. All right. So the globe valve is a linear motion stem on a globe shaped body here. So we got a valve stem that's on these. These are shaped like a globe. They have good throttling characteristics by adjusting the flow rate. They have good close off and we use these for precise control normally. Okay. It helps reduce the pressure drop for maintaining consistent system pressure. These are really tough type valves, so we use them on high pressure type applications. These are very common on air handler coils. So if you see these in the mechanical room, they're usually going to be on your air handlers. The next one we have is a ball valve, and this has a linear stem on it, but also can have a rotary stem like we see over here. So instead of a stem that moves vertically up and down, we can have a rotary stem that rotates clockwise or counterclockwise. So these ball valves are spherical shape, okay, hence the name ball. And they got a hollow ball inside to where when we open it and close it, that's how we can throttle the flow rate through that valve. These are used really good on low pressure drops, and sometimes they're used in high pressure, high temp applications. You're going to see these have good shutoff capabilities and good tight seals. And ball valves are less expensive than globe valves, but they're more expensive than butterfly valves normally, depending on the size. And you're going to see a lot of these ball valves like on VAV boxes. Those are very common, and you probably see them on air handlers, smaller air handlers. That's a common application where you're going to see these ball valves. Also, fan coil units too. You can't leave those out as well. So that's where you'll see most of these ball valve type valve bodies. Next, we have the butterfly valve. All right, so that's what the butterfly valve looks like. This is a disc shaped body here, and it's got a rotary stem. Okay, so these are going to rotate clockwise or counterclockwise, depending on how much we want to open or close these. They're going to be good on low pressure drops, and they're used on large diameter piping systems. They're less expensive than globe valves, and these are very commonly used on our hydronic plants, specifically whenever we have valve or pipe sizes larger than 4 inches or so. You're going to start seeing more of these butterfly type valves here. Okay, so let's go ahead and jump into our valve sizing. Now that we have a background in a lot of the valve bodies and the valve types, let's talk about valve sizing. Why do we do valve sizing? It's important because it ensures our hydronic HVAC equipment can handle the flow rates and also the pressure drops that are required in the system. All right. This prevents system failures. It also reduces maintenance cost. and improve system performance. If these are not sized properly, all those will be affected by that improper sizing. So, proper valve sizing takes into characteristics a few things about the fluid that's going through our valves. Okay. So, we're going to be talking about the fluid that's being handled, the viscosity. Okay. This is the measure of fluid's ability to flow. Okay. And then also the density, the measure of the mass of the fluid. And then the temperature. We got to understand the temperature. We can't use a normal, just a heating water valve or a chill water type valve body on a steam valve application. So we got to be aware of the temperature as well and how that affects the viscosity and the density of the fluid. So let's go ahead and jump into the valve sizing formula. Now, this is going to be a great part that if you want to take some notes on these formulas, if you're not familiar with valve sizing, this would be a good thing to do here. So let's go through the formula. So we have our flow coefficient. That's going to be our C of V here. And that's going to equal our Q, which is going to be our flow rate in gallons per minute. Okay. So this is going to be gallons per minute. It's going to be our flow rate. And then we have our pressure drop across the valve. That's going to be across entering and leaving the valve, as we can see here. Okay, there's going to be a certain PSI and pressure drop across there. And then we divide that by our specific gravity of water. Now, the specific gravity of water is 1, all right? But keep in mind in our hydronic systems, we use glycol mixed with water, okay? So this chart over here explains the different type percentages of glycol that we put in our water, okay? So for example, if we're looking at 40-degree water, if this is maybe on a chill water system, and we have a 25% glycol mix, that's going to be around 1.048. So that's very close to 1. So usually in our business, whenever we're doing valve sizing, we usually just use 1. But if you want to be really precise, you can include that 0.048 if you really wanted to, but it's not going to really matter that much. So we usually, in our industry, we just use 1 for the specific gravity. Even if this is 160 degrees, like a hot water system, as we can see here at 25% glycol water mix, it's only 1.018. And by the way, glycol is used like an antifreeze for our hydronic systems. Anytime you're running pipe outside your building, you're going to have insulation on it, but you're also going to want to have some glycol in that system to prevent that from freezing, because we definitely don't want that water freezing in your chill water system or your boiler. Okay, so now that we know the equation, let's go ahead and do an example. So we're going to do a valve sizing example on an air handler chill water valve. Okay, so we're going to use this on the schedule down here, air handler 1. And we're just going to do the cooling coil, the CC1. That's going to be the cooling coil valve. And so as we're looking through this, the pipe size is going to be 2 inches. All right. The valve type that we want, and we're going to say these are givens from the specification. All right. So the valve type is going to be a 2-way. We want to have a 2-way, a characterized control valve. It's going to be modulating 24 volts AC for the power. Okay. We don't want 120 on this particular project. We want 24 volts. So we're going to use our formula, all right, that we've shown before. And then we're going to look at our pressure drop. Now, if we can look on this schedule, we should have a pressure drop over here on this column over here. So whenever you're doing your valve sizing, you need to locate the mechanical schedule, because you're going to need some information while you're doing your sizings, because this is the first piece of information we're going to need is our pressure drop across that coil. So that's going to be 15. Okay. Okay, that's going to be 15. And also Q is going to be, this is going to be our flow rate. And that's going to be 189.2. So we got our flow rate in this column right here. And we have 189.2 for that. Okay, so those are going to be our givens that we need for our formula. Our specific gravity of water and glycol is 1. We can just use 1 if we wanted to on that. So that's going to be all of our givens that we can plug into our formula. So let's go ahead and put that to work here. So we'll just go ahead and plug in our Q, 189.2, divided by the square root of our pressure drop, our differential pressure drop, 15, divided by our specific gravity. That's going to give our CV of 48.8. Okay. So we have 48.8. So now what do we do with 48.8? Now we're ready to start selecting our valve. Okay. So now we're going to have to go to whatever manufacturer you're going to choose to go with, or maybe you'll get a few different quotes. But what we're going to do with that is any valve with a CV equal to or greater than 48.8 will work. All right. One thing we want to do is we want to get as close as possible on the CV to 48.8. We don't want to go lower. We want to round up. Okay. Don't ever go lower. You want to round up to the next one if it's not exactly 48.8. Okay. All right. So we go to our catalog, and as we can see over here, there's a lot of different choices for these different types of valves over here. So what we're going to do is we're going to find the one with the CV that's closest to 48.8. So as we can see, if we do this, we're going to go over here, and that's going to be, I'm going to zoom in a little bit. I'm going to make this a little bit bigger. Well, maybe not. We'll just do it this way. I was having trouble seeing this because it's really small on my screen, but as we can see here, the CV, the next highest up here is going to be 57. So we're going to want to go with the 57 CV. This is going to be a 24 volt spring return actuator. So this will fit our needs that we want as far as when we size up our valve body and our actuator. Okay. All right, so that's one way we could do it. As far as that way, we can go to the online catalog and locate, based on our close-off pressure, the closest one to that. So the other one will be, you can actually just go to the old school way where you have the catalog and you can just look at the chart over here, and then you can just pick the valve body that meets your needs over here. So we see it, the CV, the closest one we have over here is 57, and that's going to be for a 2-inch, and so on. That's going to be our B250 valve in this case, or model number for that. Okay. All right, so here's some sizing considerations for you to consider as you're going through your valve sizing. These are recommended. I mean, these are kind of rules of thumb. So whenever you're choosing your valve, you always need to round up your CV to the next closest valve choice. Don't ever round down or go lower, because that can have some serious effects on your sizing. Butterfly and ball valves are usually 2 sizes smaller than the supply line coming in. So usually if this is the supply line coming in from the chill water plant or the hot water plant, this is the chill water plant because it's blue probably. That's usually going to be 2 sizes smaller than the supply line. So if this is a 4-inch line, usually that would be like a 2-inch valve somewhat. Okay, that's kind of a rule of thumb. So if you see a 4-inch or valve and it's, you're going to be around 2 inches. If it's more than that, then might be an issue. Okay. Okay, so example, 10-inch, we got an 8-inch. Now, globe valves are usually 1 size smaller than the supply line. Okay, so if we have a 2-inch valve supply line coming in, then it could be around a 1-inch. Here's what's not recommended. It's not recommended to choose a valve less than 1/2 of the supply line. So if we reduce a 8-inch valve to a 3-inch valve, for example, that's not going to work because that's more than half. That would have to be from 8-inch to a 4-inch maximum. Okay. So that's whenever the pipe fitter is going to reduce the pipe from the chill water plant to the coil. Okay. We don't want to do it less than half the supply line. Okay. Valve sizing issues. These are what can happen if we don't size our valves correctly. Okay. So incorrect valve sizing can lead to multiple issues. Okay. These are going to include things like energy losses. All right. So that would be due to the fact that we're never really controlling our heat load in our spaces. So we're letting too much water pass through, and it's just inefficient that way. Okay. They're too small. They can't create a large enough pressure drop for enough flow to address the heat load. Too large, there's too much flow. needed by not closing off fast enough. You can also have increased maintenance cost if it's incorrectly sized. You'll get excessive wear and tear on the valve components. It's going to have to work harder due to its ability to have to cycle on and off constantly just to maintain that flow rate. Cavitation. This is a picture over here. I don't know why I didn't animate it until now, but this is an example of cavitation. This happens when we have excessively high flow rates, okay? And the physics and the nature of water when that happens, basically it creates a low pressure zone. And what happens is it forms bubbles that move up and down the stream. Okay, we have high pressure going around this disc here on the valve body, and then that's causing air bubbles to form around that and downstream. And then once those air bubbles form, they're also going to collapse within the pipe, and that can cause some great force, causing damage to the valve and the pipe. Okay. Well, that's pretty much all the podcast. I have information. I can open the floor if we have any questions for now. But I don't see anybody in the chat at this time. Let me check the chat here. All right, we have no chatters today. What I would like to do, though, before we leave today is I just want to show you. If you want to learn more about like what I covered today I covered just like a grain of sand, like on a beach, of all the stuff that you could get within one of our courses here. So we just kind of touched on valve sizing, but if you want to increase your knowledge even more, I'd recommend going through one of our programs here. We have our designer certificate that would be great that talks about things like this. These courses like these, they help us determine how to size valves, dampers, sequences, goes through the IT parts of the program and protocols and all that kind of stuff there. So check out our website. Go to smartbuildingsacademy.com to check out for more courses. And I thank you all for watching this podcast today, and we'll see you on the next one. And have a great weekend, everybody.